Okay, everything is working well. So, good afternoon everyone. I'm really glad to be back today for a second talk on a completely different topic than the one I talked to you about yesterday. So, I'm still Vincent Pradeilles, I still come from France, I still work at Worldline. The only thing that has changed is the topic, and this time is the underestimated power of KeyPaths. So, what are KeyPaths? So, KeyPaths, they are a construct that was introduced with Swift 4, and basically they are a way to defer a code to the getter or the setter of a property. So what do they look like in code? They are a generic type. It has two generic parameters. The first one is the type you apply the KeyPath on, and the second one is the type of the value that you retrieve with the KeyPath. And when you want to get a KeyPath, you use a literal syntax. It's like backslash, the name of the type, dot, the name of the property. Or in cases where the type can be inferred, it's just like backslash, dot, and the name of the property. So here you can see that I am taking a KeyPath to the count property of a string. And then, if I have an instance of this type, I can use the KeyPath to retrieve the property with a syntax that is very similar to like when you are querying on a dictionary. So here the value is 3 because my string has 3 characters. And basically what we can see is that KeyPath, they kind of perform the same job than a getter or setter closure, just with much less $zeros hanging around. So in my title, I said it's the underestimated power of KeyPath. Why this title? Is because KeyPath, when they came out in Swift 4, they looked very interesting, and then some months passed, and you could see that people were not really using them a lot, and I think it boils down to the fact that by themselves they are not that really useful, but when you add like just a few little helpers, it really unlocks a completely new realm of possibilities, and we're going to look at some examples of what we can do with KeyPaths in our code base to make our code base much swifter. So first example is going to be around data manipulation. So since Swift has released, it was a few years ago, I think we've all been used to this kind of code. So we have very generic function in the standard library to manipulate data, to do things like sorting, filtering, mapping, etc. And all these functions, they have one thing in common, is that they all work with closures. And what I want to show you to begin this talk is that with few code, with a few like syntactic sugar, we can go from this code that is quite verbose to code that relies on KeyPath and is going to be much more clean and concise. So how can we implement it? We're going to look at how we can make map, which is a very standard function, work with KeyPath. So how do we implement? First, map is defined in sequence in the standard library, so we're going to make an extension on sequence. Then we're going to implement a map function. So we can see that the signature is very similar to the map function in the standard library. The only difference is that where in the standard library you expect a function from element to generic type T, here you take a KeyPath from element to generic type T. You still return an array of type T. And inside, what do? We call the standard map from the standard library. And in the closure, we just use the KeyPath to access the attribute on every element in the sequence. That's it. You don't need to write any more code. And with this, you are now able to do things like an array of people, dot map, a KeyPath to the last name, and you get an array of the last name of all the people that are in your array. So that's the first example, that's quite nice. Let's look at something else that we do quite often, like sorting. So if you want to sort with a KeyPath, in the standard library, sorting is also defined on sequence, so extension on sequence. We write the function sorted, so a generic parameter T, we add the constant that it has to be comparable because we are going to sort using comparisons. We take as an argument an attribute for this property of type T on the element, and we return a sorted array of element. And inside, what do? We just call the sorted by function that is inside the standard library, and we just use the KeyPath to retrieve the value of the property on both the elements that the closure takes as argument, and we compare them using the less than operator, and that's basically it. With this code, we're now able to write people.sorted by age, for instance. So as you can see, the same idea basically goes for all the standard functions that you have in the library, like mean, max, sum, average, etc. So if you write all of those wrappers, you're going to be able to use this really nice syntax in your code. But even though you only have to write them once, it's still a fairly big job to do. So even if you don't want to write those wrappers, it turns out that you don't even have to. You can even go for like smarter solutions. So for instance, we said that a KeyPath is very similar to a getter function. Then why don't we try to write a function that is going to turn a KeyPath into a getter function? So we are going to call this function get. It's going to take two generic parameters, a type and a property. It takes as argument a KeyPath that are going to allow us to retrieve the property on a type. Like I said, we return a getter function, so a function that takes the type and return the property. And inside, what do? We just return a function. It takes an object as argument, and it retrieves a property using the KeyPath on this object. And with this, we are now able to use the standard function in the standard library. You can see that they are colored in blue, so they are not user-defined functions. They are the standard function that the SDK provides you with. And you can now use get and a KeyPath to work with those functions. So you can do people filter get is over 18, and you will filter out all of the people that are not over 18 in your array of person. So that's nice, but we can even go for something really shorter, and we can introduce an operator. So what is it going to look like? We are going to define a prefix operator, and we're going to use the caret character because we want it to be very short. We are going to implement this operator, so it's basically the get function that I've just showed you. Inside we are calling the get function and the signature is exactly the same. But the nice thing is that now we are able to do things like people.map, caret and the KeyPath. And basically all of the functions in the standard library that were expecting a closure, we can now pass them a KeyPath with only the added cost of one single character. So I think that's pretty cool. But as we can see, things are not always this simple, because in the example I showed you at the beginning, there was this function where it's expecting a closure, but it's not trying to retrieve a property, it's trying to perform a comparison. So how can we make this work with KeyPath in a way that's very nice for the developer that's going to use it? We're going to build another helper function, so we're going to call it this time there. You'll see why I use this name when I actually call the function. So it takes two generic parameters, a type and the value that is going to be comparable, because we want to be able to do comparison. We're going to take as argument a KeyPath to access the property that we want to sort on. We're going to take a comparator to actually perform the comparison in the sorting algorithm expects. In order to allow some shorter syntax, we're going to provide a default value, and it's going to be the less than comparison function, because that's usually what we want to use when we want to sort in ascending order. And we're going to return a function that takes two instances of a type and returns a boolean, so that's the signature for a comparison function. That's the kind of function that the sorted by function in the standard library expects as its input. So like I said, we return a function that takes two objects, and inside this function we're going to use the KeyPath to get the properties we want to sort on both objects, and we're going to compare those two properties using the comparator. So that's how you implement this there function, and once you have it, you are able to turn this line of code into this one. And the nice thing is that it reads very nicely, because you can write people sorted by their last name. It reads exactly like English, with just like the punctuation of our code, but I think it reads like really nice. And the nice thing is that you can also have, if you want to do like sorting with a custom order, like sorting in decreasing order, you can write people sorted by their last name compared with the operator that you want. So basically, I think it looks pretty nice. It makes your code like kind of very clean, very swift here. So I think we can be really glad when we have this possibility in our code base. But I don't want to stop here. I want to still keep going with seeing you how you can use KeyPath. And so to take it one step further, we're going to look at another topic, which is DSLs. And I'm interested in one particular kind of DSLs. It's the DSL that allow you to work with predicates. So just quick word of recap, what is a predicate? A predicate, it's a condition that you write using variables inside the condition, and then when you want to evaluate it, you have to provide values to substitute for those variables. So when we think about predicate in iOS development, we often think about NS predicate, which is part of the Foundation API, and it's a great API, it's been there for a long time, but the bad thing about it is that it's an API that dates from the days of Objective-C, and basically it's a strongly typed API, meaning that if I want to build a predicate that is going to filter out or filter in only the element whose first name are Bob, I have written the name of a property, the name of something that is part of my code, first name, I have written it in a string, and there is absolutely no guarantee that the compiler will be able to check if I make a typo. It's going to crash at one time, and I won't have any way to basically see it before the execution. And this is kind of bad because in Swift we like to have things be statically checked, be strongly typed, so it would be really nice if we had a way to write predicates in a type-safe way. So, for instance, in Swift you can find libraries that are going to allow you to build predicates using closures, and it enables this kind of syntax. But since I'm here to talk about KeyPath, I want to show you how you can basically rebuild NS predicate to make it work with KeyPath and still get the same level of features, but with the added benefits of type safety and statically checked code. So, to show you how you can do this, I'm going to show it to you in few steps. First, we're going to have to define what a predicate is in Swift. Then I'm going to show you how you can construct them. Then how you can combine them to build complex predicates. And finally, how you can evaluate them to actually make them work with your data. So a predicate, like I said, it's a condition that is expressed using a variable, and when you want to evaluate, you provide the value of the variable. So how does this translate in Swift? Pretty simple. It's a generic type predicate. It has a generic parameter called element. Inside, it stores a condition, so it's a function that takes an element and returns a boolean, and it has a function that you can call to evaluate the predicate by providing a value for the element. So this is pretty straightforward. Let's go to the next step. So how do you build a predicate? For instance, how do you build a predicate that the age has got to be lesser than or equal to 22? You do this by implementing an overload for the operator that you want to use in the predicate. So here the operator is lesser than or equal. So I'm going to implement an overload for this operator. So this is an operator, so it takes two arguments, its left-hand side and its right-hand side. So the left-hand side is a KeyPath, as you can see. It's the age KeyPath. The right-hand side is a constant. It's the integer 22 here. And of course, since I said that I am using this function to build a predicate, it's going to return a predicate. And inside, what does the implementation look like? It's actually pretty simple. So I want to return a predicate, so I need to call the initializer of predicate. It takes a condition as an argument, and my condition is that I have a value, and in the function, I'm using the KeyPath to get the attribute on the value, and I'm going to compare it with the constant. So it's pretty simple. If you want to be able to build predicates for other operators, so for instance, in the second example is the greater than operator, you just implement the appropriate operator, and the ID is exactly the same. It's just the operator that you use in the condition that you pass to the predicate initializer that's going to change. And with this, you are able to build like atomic predicates. So then the next step is we want to be able to combine predicates using logical operators, so things like AND or, because we want to be able to build like complex queries. So the idea is the same than before. We are just going to provide an overload for the AND operator. This time it's going to take two arguments, so both its left-hand side and its right-hand side are predicates, and it's going to also return a predicate. And inside, what do? We just instantiate a new predicate, and we evaluate the left predicate, the right predicate, and we do a logical AND between both the results. And this way we are now able to combine predicates. And finally, when we want to evaluate them on our data, we're going to do like we did for the function that we are wrapping like map and sorted. We're going to define an extension on sequence. I'm going to define a function that's going going to be called select where predicate. And inside, I'm just going to call the standard library function filter. And as the test to see if the element must be included or not, I'm going to evaluate the predicate for this element. And that's basically all you need. With the code I've just shown you, you are able to write code like to only select in an array the elements where you've got the people where the age is less than or equal to 22 and the last name has more than 10 characters. But if you implement more operators as you go, you will be able to do more complex stuff. For instance, you could be able to compare some properties with respect to a range. You will also be able to use predicates to find the first element that satisfies a given condition, or even to check if there is an element that satisfies a condition. And actually, if you feel like it, you can even go for more fancier stuff. For instance, you can implement the pattern matching operator, so it's the tilde equal operator, and you're going to implement it as it's left with, as a left-hand side, a predicate, and as a right-hand side, an element. The implementation is very straightforward. You evaluate the predicate by providing the element, and with this, you unlock the ability to switch on a value, and inside your cases, you can provide a predicate. So, as you can see, this basically unlocks the possibility to do some kind of complex pattern matching because you're able to express basically any condition that is possible to express since you have the basics building blocks, which are the operators and the logical operators to combine. So, pretty nice stuff. We've seen that when we want to manipulate data, KeyPaths are a pretty valuable asset. But I don't want us to stop there. I want us to keep going and let's look at other possible applications. So we're going to look at how can KeyPath enhance existing design pattern. So the first pattern that I want to talk to you about is called the builder pattern. And its goal is to provide separation between building an object and using an object. So in our code, we often find things like this, where we instantiate a value, then we configure it, and then we use the value. And what we like to do often when we structure our code is to separate clearly the part where we are building the object and the part where we are using it. So it makes the code much more legible. But the thing is that semantically, those two things are very different. Building a value and using a value is not the same thing. And the only thing that's separating them is like a white blank line, and it's not very strong. So what I want to show you is that with KeyPath, you can do something like this. You can define a protocol called buildable, so very simple protocol. It's empty. You define an extension for buildable that is going to add some method when the object that conforms to it is any object. So basically when it's a reference type. And we're going to define a function called with. So it's a generic function. It's going to take a writable KeyPath to a property and a value for this property, and it's going to return an instance of self. And inside, okay, so I was planning to go into more details, but I've just said it. And inside, what we're going to do, we're going to use the value to set it on the instance, so on self, and then we're going to return self. Then we make NSObject conform to this protocol so that we can actually use it. And now with this, we are able to write this kind of code where we can instantiate an object, chain several calls to the with function where we say with text color set to red, with text set to this string, etc., etc. And this way, we now have a very clear and a very visible separation between when we are building our object and when we are using it. And we are no longer running the risk of people misunderstanding and putting a line of code that is not appropriate somewhere between the building parts, because the compiler will tell us that there is a mistake in our code. And it's also very clear to a person that finds our code that there is two parts, the part where you build the object and the part where you use it. So let's look at a second pattern. So it's something called the Identifiable Pattern. And basically, the idea with this pattern is to enable equality based on an ID. It's kind of useful when you have a server or a database where you want to be able to say if those two objects have the same ID, then they are equal regardless of whatever their values can be, the ID is the only source of truth for equality. So what is it going to look like in code? So we're going to define a protocol called Identifiable. It's going to inherit from equatable. It has an associated type ID, so it's the type for the property that is going to be the ID, and it has, of course, to be equatable because we want to compare equality based on it. And it's also going to have a static var, which is going to be the key path for the ID property. So using this protocol, we write an extension where we implement the equality operator. So inside this operator, we are just going to do the comparison using the key path for the property that is the ID. So it's kind of straightforward. And then the interesting part is when we actually want to use this protocol in a type. So here I have defined a struct user. So it has two fields, a first name and a last name, and a third field which is the ID. And it's also going to declare the ID key path protocol requirement from the identifiable protocol. And it's going to say that the field that you need to use as an ID is user.id. So it's, does it work? No, the pointer doesn't work. But it's the let ID string. So now if I build two users in my code and I try to compare them, so it's going to tell me that user 1 is not equal to user 2, and that makes sense because they have different IDs. But if I build a third user and it has the same ID than user 2, and I try to compare the both of them, it's going to tell me that yes, they are the same because they are basically sharing the same ID. So using this protocol, we are now able to compare types based on an ID, and our types, as we saw, were like really simple and easy to write, and we didn't have to provide like closures to get the property that is going to be the ID, like we would have to do like in version of Swift that were prior to the introduction of KeyPaths. And so to finish like this overview of what you can do with KeyPaths, I want to talk to you about a third pattern. So it's called the Validable Pattern. And the idea is that it will enable you to perform some property-wise checks on an object. So to implement this pattern, we're going to define a struct. So it's called a validator. You'll see that it's quite similar to the predicate struct I've showed before. So it has two fields. It has a valid, which is the value that you want to validate, and the validator. So it's a test that takes an instance of the validity and going to return a Boolean to indicate whether or not the test was passed or failed. And it has a function validate, where you just call the validator by providing the validity. Then we define a protocol named validable. So like the one before, very simple because it's just empty. We write an extension of this protocol, and inside we add a function that is going to allow us to add a test to a validable type. So the function is called add. It has a generic type, which is the property that we want to validate. So it takes a validation test, so it's a closure from a property to a Boolean. And since you need to apply this validation to a property, you're going to provide also the key path to retrieve the property. And this function is going to return a validator. So inside the function, we just instantiate a validator. We say that the validity is self because it's an instance method and we have access to self. And inside the validator, we're just going to use the key path to retrieve the property. And we use the validation that was passed as an argument to check whether or not the condition is met. We also have to implement an extension on validator. So it's basically the same function that I've showed you. The only difference is that this time we are not going to build the validator from an object. We are going to build it from another validator. The idea that this will like allow you to chain validators, to add several validators. So inside, we just build a new validator. The validity stays the same, and for the condition, we evaluate the current condition, and then we evaluate a new one, and we do an AND between both of the conditions. So basically, we're like doing some sort of linked list of conditions that is going to be reduced with the AND operator. And then on our code, so if once again I define two users, I make the type user conform to validable. I'm now able to write code like this. So I have my user 1, and I want to add a first validation that its ID is not empty. and the second validation that its last name is equal to the string Lennon. And if I call validate, it will tell me that the validation went well because every single one of the validation conditions were met. On the other hand, if I write the same validation test for the user 2, it's going to tell me that no, this second user did not pass the validation, probably because the second condition was not met. And of course, I've used closures to express my condition here to keep the code like short and legible for the slide, but this is of course a very good place to use predicate-based syntax for expressing the condition. So what have we just seen? I've showed you that basically KeyPaths are a pretty nice tool. We can use them in several contexts. We can use them for data manipulation. We can use them for several design patterns. So I think there was a lot of content in this talk. So before we end, I'm going to do a few recaps just to provide you once again with the main ideas. So what is it that you can take away from this talk? You can take away that KeyPaths, they basically offer a way to defer the reading or the writing to a property. So they're kind of like a getter or setter function. And you can also keep in mind that they allow for very clean and expressive syntax inside your code, because like I said, they do the same work than Clojure would, but you don't have to have all the $zeros, $1 hanging around, you don't have the curly braces, etc. They work very well with everything that is generic, so the example that I've shown you, it were things like functions like maps, sort, filter, so these are generic functions, and it was also like generic use cases like validating values or testing that objects are equals based on an ID. So basically whenever you have generic algorithm that involve testing things with the property of a value, it can be a nice hint that KeyPath can bring some value to your code. We've seen that they are a really great tool to build DSLs. For instance, the Predicates DSL, I think it works really, really well, and you don't have to write that much code to make it happen. And basically, they offer some nice sugar syntax to many patterns, meaning that KeyPaths are not going to bring you features that you didn't have before, but you will get the same feature with less code, and the code that is also more legible, more expressive, and that can like read more like natural language than computer code. So in conclusion, I think you've understood that my message is that KeyPaths are great and you should really try to use them in your code. I have a big thank you to two of my French colleagues, so Marion Curtil and Jérôme Alves, because their input to the content of this talk was very valuable. And if you like what you saw and you want to see some more ways that you can use KeyPath or how some more complicated use cases can be implemented, I have a repo on GitHub that you can absolutely go browse, and I think you will find things that will interest you if you like the content of this talk. The slide, I'm going to post them on Twitter, like I think during the next hour, so you will have all the links that you need. And that being said, once again, thank you for having me here for both days, and that's all.
Thank you, Vincent. We've got a couple of questions.
Okay, so first question, do KeyPath have any performance penalties? I assume it would be slower than direct method calls. That's a good question. So I'm not 100% sure of the topic, but my understanding is like if you take a KeyPath to something that is a stored property, it's going to be kind of fast because the compiler has the ability to like substitute the KeyPath with like direct access to the value in the memory layout because it knows the memory layout of the structure. If you take a KeyPath to a stored property, I think the compiler is going to turn it into a function call. I'm sorry, if you take a KeyPath to a computed property, I think the compiler is going to turn it to a function call because computed properties are basically function calls in disguise. So I don't think there is a performance issue. And of course, if you take a KeyPath to something that is at Objective-C, it's going to turn it into an Objective-C KeyPath, so you will get the exact same performance than you would. So I would say at best it will be better, at worst it will be the same. And the second question is, what is the impact of using KeyPaths in compile time, using KeyPath for configuring a label versus grid with direct accessors? That's a very good question. I did not run a benchmark. I would say that if the KeyPaths makes the compiler use type inference, there could be some penalties. That being said, I don't think that when you use KeyPath, you run into the more like complex cases of type inference. So I think it will be like very, very small, but I might be wrong on this. And last question that just appeared, can we use KeyPath to expose some private vars? I don't think that you can, because it's going to be statically checked by the compiler, so I don't think that you can. The only place where you will be able to do it is like for things that is Objective-C compatible, but once again, you can already do this without KeyPath, so I don't think it brings new values for this problem.
Thank you so much, Vincent. Let's give him a round of applause.